The introduction experiment shear force beam. The structure are built to accommodate, carry and transmit load. Commonly built structure are beam, column and trusses. When a beam is subjected to a force, it causes the beam to bend and undergo vertical displacement, elastic deformation. Vertical displacement tends to shear the beam. Shear refers to the relative moment between two parts of a structural member. Any beam must be designed so that it can withstand shear. The purpose of this lab is to demonstrate the principle involved when determining shear force in beam. There are two experiments involved. The purpose of the first experiment was to measure the variation in shear force with increasing point load, while the purpose of the second experiment was to measure the variation in shear force for various loading conditions. At the end of the lab, we should conclude the shear force at the cut point is equal to the algebraic sum of the forces acting to the left or right of the cut. The objective shear force in beam: one, to examine how shear force varies with an increasing point load. Second, to examine how shear force varies with an increasing point load. For this experiment, we used theory. For the part 1, we use the equation. Equation 1, shear force at left the section. Equation 2, shear force at the right of the cut section. For the part 2, we use the words the shear force at the cut is equal to the algebraic sum of the force acting to the left or right of the cuts. For the methodologies, shear force in beam, the apparatus and equipment as per shown. And second, the procedure. Part 1, 1, the digital power display meter is checked for a zero value with no loads. Second, a hanger with a mass of 100 grams is placed to the left of the cut. Third, the reading value on the digital power display is recorded in table 1. Shear force on the cut Newton as display force. The test is repeated using a mass value between 200 gram and 500 gram. Mass value are converted into the load in newtons for calculation of the theoretical shear force on the cut made before table 1 is completed. For the second part, we follow one digital force display meter is checked to zero value with loads. Second beam are loaded with hanger carefully by following the position as in figure 3, figure 4 and figure 5, and the table 2 is completed. Third, the reading on the digital force display is recorded where shear force on the cut Newton as display force. For supported reaction, reaction A and reaction B are calculated, and further calculation theoretical shear force on the cut is implemented.
In the experiment shear force in a beams, I will present my part, which is the result and data analysis. So for the part, this experiment we have done the two part. Which one is the part 1 and part 2? Part 1, which is the west once is located at the 140 mm left of the cut. So the data analysis will be shown in the table. So the table have the 5 column. Which one is the column 1 is mass, the column 2 is root, and the column 3 is the force. And we compare to the experimental shear force and the theoretical shear force. So you can see clearly we use the different mass and the force will be different in the shear force will be different acting on the beams. Moving on to the experiment part 2. Part 2 we have the 3 cases. Case 1, the west one is located as the 140 mm left of the reactions A R1s. So since the west is at left hand side from the cut, so we use the formula equal to SC equal to W times the length minus A divided by the length. So we can see clearly the small letter a is the distance from the west from the RA, and the length is the total length of the beams. So we can get the RA equal to 2.58 newtons and RB equal to negative 0.62 newtons. Moving to result data analysis part 2 case 2 experiments. This one, the differences between the part 1 and part 2 is the wedge. The distance of the wedge from the RA is different. In part 2 experiments, the A distance is equal to 220 mm and the total length also the same. So, but the distance from RA to W to the second wedge is the 260 mm. Since the wedge is at the left hand side, so we use the same formula, which one is the SC equal to wedge W times the length minus A divided by the length. So we can clearly get the shear force is 0.9x. Hence we apply the same formula, which one is the total vertical force Fy equal to 0 and the bending moment at the point A equal to 0. So we can see clearly using the formula, the basic formula, we can see clearly Ra equal to 1.28 newtons and Rb equal to 2.72 newtons. Moving to result data analysis part 2 case 2 experiments. This one, the differences between the part 1 and part 2 is the wedge. The distance of the wedge from the RA is different. In part 2 experiments, the A distance is equal to 220 mm and the total length also the same. So, but the distance from RA to W to the second wedge is the 260 mm. Since the wedge is at the left hand side, so we use the same formula, which one is the SC equal to wedge W times the length minus A divided by the length. So we can clearly get the shear force is 0.9x. Hence we apply the same formula, which one is the total vertical force Fy equal to 0 and the bending moment at the point A equal to 0. So we can see clearly using the formula, the basic formula, we can see clearly Ra equal to 1.28 newtons and Rb equal to 2.72 newtons. So after we complete all the experiment part 1, part 2 and part 3, we finalize all the value and we record in the table. So we can see clearly the experimental shear force is the biggest and maximum in the case 1. So this one is the 1.6 newtons, and the theoretical shear force also is the case 1 will have the 1.34 newtons, and the lowest shear force will is case 3. This one that we get the result from the experiment is 0.6 newtons shear force, and the theoretical shear force is 0.89 newtons. That's all for the result and the data analysis. All the value we have record in the table as the reference.
So we move to discussion, part 1. Number 1, derive equation 1. Let moment MB is equal to 0. So Ra times L minus W times L minus A is equal to 0. So we get Ra is equal to W times L over A. Since the force at the cut is equal to the algebraic sum of the force acting to the left or right of the cut, therefore SC is equal to Ra, SC is equal to W times L minus A over L. Let summation of MB is equal to 0. So RB times L minus W times L over A is equal to 0. So RB we get negative W times A over L. Therefore, SC is equal to negative W times A over L. So W is load, A is the cut section from RA, L the length from RA to RB. By using this theory, the value of shear force can be found using this equation. W is load of the length A that is applied to the cut segment. L is the sum of distance from. So next question. Plot a graph which compares your experimental results to those you calculate using theory. So for my group, we get both the experimental shear force and theoretical shear force increase. Number 3, comment of the shape of the graph. What does it tell you about how shear force varies due to an increased load? From the shear force versus load graph we plot in this experiment, a non-linear graph was obtained for both experimental shear force and theoretical shear force values. Both graphs are non-linear and go to the coordinate 1, 0, which tells us that shear force does not exist when no load was applied on the beam. From the graph, we can know that when the load applied on the beam was increased, the shear will also increase. This indicates that shear force is not proportional to the load applied on the beam. So lastly, does the equation you use accurately predict the behaviors of the beam? So the answer is yes. The equation is SC is equal to W times L minus A over L that we use for the experiment is theoretical shear force calculated accurately predicts the behavior of the beam. It is because from the graph we plot, we know that the load placed at the beam is increased.
The experiment revealed the significant discrepancy between the theoretical and experimental values, with the significant difference in influence line values. The machine multifunction could be cause indicating that its correct procedure was followed, but machine condition may have been compressed. The experiment demonstrates that the shear force at the cut is not equal to algebraic sum of the force acting to the left or right of the cut, and that distance affects the bending moments when examining in various percentage. Experiment shear force versus load graph show the non-linear relationship between the experimental and theoretical shear force values. The graph, which goes through the coordinate 1, 0, indicates the shear force does not exist when no loads are applied on the beam. However, as a load on the beam increases, the shear also increases, indicating the shear force is not proportional to load applied.
Our group used the results of this experiment to investigate how shear force changed as the point load increased. We also investigate the variation in shear force at the beam's cut position under different loading scenarios. We conclude from the first experiment that the shear force will rise proportionally to the beam's load. As a result, we deduce that the shear force is positively and linearly proportionally to the load acting on the beam. We infer from the previous two tests that when a load was applied at the cut, shear force typically manifests at any location of the beam. Our group created the GDR graph for this experiment to illustrate this observation. The experiment's outcome also shows that the force operating on the beam at the left and the right side of the cut section equals the shear force at the location.